Okay, so we're on to 3F, rates of change, and this is going to be a nice little easy exercise before we move into optimization. We've got here 2 questions to get through. We're going to use our calculator a fair bit, and we're going to even draw out some of those relationships we talked about in 3D. So we'll just get straight into the question, because I think all of the new stuff here is fairly intuitive, so we don't need to explain anything specifically. Actually, maybe we know, right, that if we have f of x, then f dash of x describes the rate at which f of x changes. So in this example, we have the height of a tree with regards to time. So h dash of t is going to describe the rate at which the tree grows. Okay, so that's what we're doing in rates of change. All right, so we have the height of the trees given by this equation here. Part A, how high is the tree initially? Now we're going to answer both of these to 3 significant figures. All right, so in a test, we'll be very specific. It's always round to 3 significant figures unless otherwise stated. And sometimes they might ask you to round to 2 decimal places or 3 decimal places or the nearest integer. So you're expected to know what those mean. We will round these to 3 significant figures. Now we have how tall is the tree initially. Now that means when time is 0, so we're finding h of 0, and that's 12 on top of 1 plus e to the power of 5. So that there, we've got a couple of procedures we could do. Now with a question like this, in my mind, you can type that into RunMat if you want, but we can see we have to do it in a moment for when time is 6, and then we have rates of change in part C. So I reckon the best way to do this is to graph that function and then just g-solve those points on it. G-solve, because then you're not typing, you don't have all this syntax that you're typing in. So remember, we're always looking at the optimal, the most efficient, the most economic process as far as time is concerned. So let's graph this function. And we're talking about time on the x-axis, which means we'll only consider positive values of time, right? So when you're starting to develop your v-window, if you're looking at this function, you won't have an immediate idea of what v-window to set. But we're going from x-min to x-max, y-min to y-max. But we do know that x-min we don't consider negative values of time. So our lowest value of x will be 0. The height of a tree, it can't be negative, so the lowest value of y will be 0, which means we're looking in the positive quadrant, right? And so from then on, sometimes the model can tell you a bit about it if you're familiar with the model. Otherwise, I just recommend the trial and error approach. Frequently in a test or exam, we give you a Cartesian plane if you're required to sketch it. And so then that tells you the parameters on the plane that you're presented with. Okay, so let's just go for our v-window. I'll show you what I mean by trial and error approach. So let's just set our x max as 10 and our y max as 10, and we'll graph that function. And it is pretty good over that interval, but perhaps we could up the y a little bit. So we'll just change our y max to 15. Okay, and we can see the function there. All right. We've got how tall is the tree initially, so we want to know h of 0. And so what I'm going to do is trace along. So I'm pressing F1 for trace, and I'm going to press when x is 0. So that takes me to the y-intercept. We've got the y value 0.08031. All right, so for 3 significant figures, what we're going to do is write the first 4 figures after the zeros, so the first 4 figures, and then we round the 4th figure, 803, and our unit is meters. All right, so that's about 8 centimeters tall. 3 significant figures? No, that's 3, because the 3 significant figures are after the zeros. So we have 2 zeros here, and these are the 3 significant figures. Yeah. So we keep writing zeros until we get to the first figures that are non-zero, and then we write those 4 figures and round the 4th one. All right, okay, after 6 years, so this is h of 6. Now we can obtain this by putting the number 6 into this equation. So what it would be, 12 on top of 1 plus e to the 5 take 6, but we're just going to g-solve it. Again, pressing trace, and we'll go to x is 6, and the corresponding y value is 8.772, so 4 figures, and we round the fourth, 8.77 meters. So we've got part A complete, part 1 and part 2. Alright, pretty basic stuff there. Let's move on to part B. Discuss as t approaches infinity. Now, there's two ways to do this. One is to make an algebraic argument, which I'm going to do up here. The other is to look at the graph and just trace along it. Alright, so if we trace along it and we move to higher values of x, we can see that it's approaching a limiting value. 11.8, 11.9, it's getting closer and closer and closer to 12. And that's fascinating. I'll point out in a moment, this type of model that we have has a limiting value at 12. Okay, so let's do it algebraically. What's going on as t approaches infinity? So as t approaches infinity, as t gets large, we break it down into the variables. So the variable is here, isn't it? E to the power of 5 take t. E to the power of 5 take t, if we put a really large number in here, we have, let's say 1,000. Okay, if we have 5 take 1,000, if we did that, 5 take 1,000, that would be e to the power of minus 995. Too many numbers there. Which is the same as 1 on top of e to the 995. Right? Now, 1 divided by, this is an enormous number, e to the 995. So if we have 1 divided by an enormous number, this component is approaching 0. So this is to say, as t approaches infinity, this component approaches 0. It's getting smaller. All right? So if this is approaching 0, then the height of the tree is approaching 12 on top of 1 plus 0, which is 12. The height of the tree is approaching 12. All right? So we can observe that from the graph. Okay, part C. At what rate is the tree growing initially? So we've got two ways we can answer this. We can find the h dash of t function, and we're going to do that in order to show you what it is and how we're doing it. H dash of t describes the rate at which height changes. So in order to differentiate this, first we're going to express it like this. All right, and we have a number times a function to the power of minus 1. So we're going to use the chain rule. So it's going to be our n, the function, n take 1, and then multiplied by the derivative of the function, which will be minus e to the 5 take t. Alright, so that's the derivative function, h dash of t, and we want to know what's the rate, what rate is the tree growing at, what rate is the change initially. So that's going to be h dash of 0. So we could obtain that by putting 0 into this equation, right? That's going to be the long way to do it. Okay, we can show that's how we obtain the calculation, and you can manipulate this to make it more pretty if you want, but that's fine as is. So we could put 0 in here and here. But when we go to typing it in our calculator, I reckon we don't type any of that in. Look how long it is. Very easy to make a mistake with a bracket and a power. Instead, we just g-solve it again. And when we're tracing along on our calculator, if we've got the derivative mode turned on, then it will tell us the dy and dx when x is 0, and I've got 0.0797. And it hasn't given me a fourth figure, so it's rounded at 4. So we trace F1, and we press x is 0, and we've got the y, the dy and dx. dy and dx. Yeah, shift. Oh, you did a y cut, did you? No, don't do that. Go trace next to zero. If you do a y cut, it doesn't pop up. Help anyone else that needs this? Oh, sorry. No. What I'm saying is in this mode, we press trace and see how it's picking up d1 dx, and then when time is 0, and let's just slope. Yeah. What's going on when you do with that? What have you done there? Oh, you haven't got an x. That'll mean definitely need an x for the variable. Is that any good?
Yes.
Excellent. Darcy?
Mm-hmm.
Good. Ella? Excellent. Okay, cool. So that's h dash of 0. Next we're asked for h dash of 2. Now, sorry, we should put a unit here. And our unit is the y-axis per x, right? Rate of change is always y per x. On the y-axis we have meters, and on the x-axis we have years. So initially the tree is growing at 8 centimeters per year. Pretty insignificant. How about after 2 years? So h dash of 2. Let's evaluate that one. So we'll go when x is 2. What's the rate of change? And we've got 0.5691. Oh, sorry, I'm reading the y value. 0.5421, which is 0.542 meters per year. All right. Part D. When is the tree growing at its fastest rate? So I just want to recall something, all right, from 3D.2. Really important, the bottom row of the table, it says points of inflection on f of x correspond with maximum and minimum on f dash of x, the turning points. Okay? So that means the rate will always be maximized at a point of inflection. Now there is a point of inflection on this graph. Here's what our graph looks like. Okay, it's doing that kind of thing. And so there's a point of inflection somewhere here where it changes from being concave up to concave down. So we need to find that point of inflection. Now I think the easiest way for us to do this is going to be to graph the derivative function. Let's graph them both on the same axes. So we can go option calc d on dx of y1. So we can make it graph the derivative function for us. And we can see both functions there. The derivative function looks so just doing this kind of thing. And that maximum corresponds with the point of inflection. That's when the rate of change is maximized. So if we g-solve the maximum on the second function, we're just asked, when is it maximized? It's maximized when t equals 5. So after 5 years, the tree is growing at its fastest rate. All right. So point of inflection on the original function will correspond with the maximum or minimum, a turning point, on the derivative function. Okay, any issues with that one?
What are we typing into here?
So we graph the original function and the derivative function. So in y2, I just sketched d on dx of y1.
Mm-hmm.
Yeah. Very good. Yeah, that's the opposite way of saying it. Yeah. Absolutely. Is that any good? Yes. Maggie, good.
It's just
T equals 5 is our answer. Yep, 5 years. If we're given a context, we should always use the unit that we're given. All right. Okay. Let's move on to the next question then. So again, we use our calculator to help us out. We have the volume of water, kiloliters, in a tank t minutes after the valve is open is given by V of t equals, we have this logarithmic equation, minus ln of 0.1 t plus 0.5. All right, how much water was in the tank initially? So this means V of 0. So we're going to put 0 into this equation. evaluate that to 3 sig figs, or we can look at the graph. Just type this in, minus ln of 0.1 times 0.5, 2.995. Okay, so if we're going to 3 significant figures, right? 2.995 is the first 4 figures. The 5 rounds up, which means 9 rounds up, which means the other 9 rounds up, which means we get 3 kiloliters. So 3.00 kiloliters is the 3 significant figures there. All right, part B. When is the tank fully empty? Well, the tank will be empty when the volume is equal to 0, won't it? So part B, empty when the volume is 0. So that means minus ln times 0.1 t plus 0.5 equals 0. Alright, so if we're going to solve this equation, what we'll do is first get rid of the negative. We'll divide both sides by minus 1. Alright, t plus 0.5. And then we'll raise e to the power of both sides. So when we raise e to the power of both sides, e and ln will cancel. E to the power of 0 on the right hand side, that will simplify to 1. And I'm not going to expand that. Rather, I'm just going to start by multiplying both sides by 10. So if we multiply both sides by 10, on this side we'll have t plus 0.5, and on this side we would have 10. Alright, which gives us t is 9.5. So after 9.5 minutes, the tank is empty. Okay, so hence state an appropriate domain for the function over which it's valid. Well, it's going to be valid between 0 and 9.5 minutes. Now, if we are given a domain over which to operate, we must operate within those parameters. We can't operate or answer anything outside of those parameters. If we're required to graph it, we would only sketch it over that interval. All right, so it would be wrong for you to graph the volume of a tank and then have negative volume. All right. Okay, what is the volume after 4 minutes? This just means V of 4. All right, so we'll put the number 4 into our equation here. Minus ln 0.1 times 4 plus 0.5. And we'll evaluate that in a moment. When is there 1 kiloliter of water in the tank? Okay, now here you've got 2 strategies. What you could do is, when we're solving this, when is the volume 1 kiloliter? So it's when this t plus 0.5, sorry, exaggerate that t. It's when the volume equals 1 kiloliter. Now, if we've got the graph function, we can do a g-solve and we can do an x-calc when the y value is 1, and tell us the corresponding x value, or we can perform the algebra. All right, let's do the algebra. What we're going to do first is divide both sides by -1, so move the negative over. Then we'll raise e to the power of both sides. So that's going to be e to the power of -1. Then we'll times both sides by 10. And then we'll take 0.5 from both sides. Alright, so that is the exact value of time. Remember, sometimes we're asked for the exact value. If it's exact, then we definitely have to perform the algebra. If it's not exact, then we can just, use technology and to G-solve it. Alright, so we'll give all of these things an answer, I think. Let's have a sketch of the function. So if we go into our graph mode, we've got minus ln of 0.1 and then brackets x plus 0.5. Okay, now we know for x that it's restricted to 9.5, between 0 and 9.5. And we also know that the initial volume is 3 kiloliters and that water is leaking out. So all of the constraints for our graph are implicit in this question, right? We found the domain and we know the maximum volume because water is leaking out. So x min 0, x max 9.5. Y min 0, Y max 3. And we'll have a gorgeous graph there. Okay. And then we can G-solve all those numbers if we want to, get them exactly and so forth. So we can go, all right, when x is 4, what's the Y value? We've got 0.7985. All right, so that will round to 0.799 kiloliters. After 4 minutes, there's 0.799 kiloliters. So, I reckon we don't have an x in there. You need another bracket. What it's doing is it's calculating ln of 0.1 and then doing the equation for y. So yeah. Anyone else? Okay, so let's G-solve those points. So we've got the volume after 4 minutes. We can G-solve, do a x calc when the y value is 1, and that's 3.17, 178, so 3.18 minutes, because here we calculated the t value. All right. What else? Is there anything else we haven't evaluated? Looks like the rest is good. Okay, so we're on to part E, and it says determine at what rate is water leaving the tank initially and when time is 6. So this means what's volume dash of 0 and v dash of 6. So we could find the derivative function here. All right, now I'm going to do it just so that we can recap derivatives of logarithmic functions. If we have ln of f of x, okay, then the derivative is f dash of x on top of f of x. Now I'm going to break this function down as well because I'm going to try and draw out some of these log laws. What we have here is we have ln of 0.1 times t plus 0.5. Now if we have ln of a times b, we can split it. It becomes ln of 0.1 plus ln of t plus 0.5. Whenever we can see log laws, we should split them. All right, we've got that negative at the front, or you can apply it to both of them, it doesn't really matter. All right, so we've just split that logarithm. So this is the volume function, another way of presenting it. And so now when we differentiate it, it's going to be super easy. That the negative can hang out the front, and we'll just keep a bracket there. ln of 0.1 is a number. So when we differentiate it, that part's going to 0. And so then we're just looking over here, and we're differentiating that part. ln of, it's a linear equation, so when we differentiate it, we'll have 1 at the top, and at the bottom we would have t plus 0.5. So that's our derivative function, minus 1 on top of t plus 0.5. All right, so to find v dash of 0, we can put it into our derivative function, or we can solve it from our graph. I'm just going to go from my graph. When time is 0, the dy on dx is minus 2. And when time is 6, the dy on dx is minus 0.153. And the unit here is kiloliters per minute. Kiloliters per minute. All right, y per x, always y per x. And on our y-axis we have kiloliters, and on our x-axis we have time in minutes. Okay, so both of those have been answered. Talked about that. All right, there's one more part over the page. Root equals 6. V dash of 6, yep. Okay, now the part over the page says, when is water leaving the tank at the highest rate? So we should be thinking, all right, when is the rate of change maximised? Well, the rate of change will be maximised at a point of inflection. And if we look at this graph, here's what it looks like. There is no point of inflection. All right, there is no point of inflection. So then we have to go, well, when is it steepest? When is the graph steepest? And if you look, what's going on is it starts off steep and then gets shallower and shallower and shallower. Its rate of change is decreasing as you go on. And of course, we expect this in the context of the problem. If you open a tank up when it's full, all right, there's all that pressure forcing the water out, but as it gets lower and lower, the flow rate reduces because there's not as much force from gravity pulling the water down, forcing it out. Okay, so it's going to be when time is 0. One more way that we can observe that, right, is we are asked, when is the rate of change maximised? So what we'll do is we're going to sketch the derivative function. So we can sketch this one, or we can go d on dx of y1. Now, the derivative of y1 is going to have negative values, okay, which means we need to adjust our v window to include negative y values. So I'll just change my y min to -3. And what we can see, this function looks like this, all right? And this is the rate of change, and we're saying, when is the rate of change largest? When does it have the largest size? Well, it's furthest away, its maximum distance from the x-axis is here, isn't it? That's when it has the largest rate of change. That's when the dy and dx is furthest away from it. So we can observe it from the derivative function, or we can even just observe it from the initial graph. That's when it's steepest there, and then the rate of change is decreasing. We can observe that feature. The rate of change is decreasing because as time increases, the rate of change gets closer and closer to 0. We can see that on the derivative function. So all of those features correspond with one another. All right, I've talked for too long. Let's get, one more thing. On page 53, we have types of models, okay? Now, these kinds of models will pop up in the following exercise, and if you want, it's something you can memorize, but I think what's probably better is just knowing how to differentiate different types of functions. But they're here, and there's properties of those models there. Some schools do their whole folio task around these models. We don't, we do ours around the integration techniques, but it's not something that we need to teach explicitly, but it's there and they will pop up in some of the questions with the properties of the models. I think even in some parts of 3D.1, you end up proving some of the properties of those models. Does that ring a bell? Yeah? Okay, so 3D1, looking at question 13 is the surge function, 14 is the logistic function. So they pop up in 3D1. All right, so just wanted to point that out. So 3F, use your calculator to support you, use the calculus techniques.